Okay, good evening everybody. Welcome to our last presentation before Christmas. Nice to see a couple of Christmas jumpers out there, well done. So quite a few things to get through this evening, and before the main presentation we're going to have a little presentation on tunnel skills or competencies. So to introduce our speaker tonight, I'd like to ask Ian Heath to come up.
Good evening. Earlier this year, Tunnel Skills was approached by a chap called Alistair Reisner, who is the Chief Executive of the Civil Engineering Contractors Association. They're called SECA, if you didn't know. They've been tasked by the Construction Leadership Council with establishing competence within a regulatory framework across the construction and the built environment sector. This requirement is a response to Dame Judith Hackett's recommendations on competence following the Grenfell tragedy. Tunnel Skills have agreed to assist in the process on behalf of the tunnelling industry. So, I'd like to introduce Faye Burnett, who is the Programme Director for the Construction Leadership Council Installer Competence Programme, who will explain what we all need to do. Faye, over to you.
Hello, it's a lot of you. Be nice, thank you. Thanks for having me. So my name is Faye and I work at MACE and at the Construction Leadership Council. I've put my two colleagues up on the screen because we do a lot of work with the Super Sector Programme, that's what we call it, the Super Sector Programme. There's about 600 people across industry working on this programme, including Tunnel Skills. So I just wanted to highlight how many of us. There are only 3 of us, so it's a lot of work. The building safety regulator has said that is our regulatory body for competence, and competence is now enshrined in law. So if you say, why are we doing this? We have to do it. It's a legal requirement. And it says that competence for an individual is having skills, knowledge, experience, and behaviours. I'm going to say SCEB over and over again. Skills, knowledge, experience, and behaviours. This is what competence is defined as. Why we're doing this is on a higher risk building, all those working in or around a higher risk building will now be audited on their competence by the building safety regulator. This is a new thing, it's going to come in next year. The building safety regulator has also said that they're going to use our competence frameworks as the baseline for auditing competence. So the work we are doing will help improve competence in our industry across the board. And on all other projects, the building control body will be auditing competence. I'm going to go through these slides quite quickly. I've got 15 minutes, but I'm going to give you the slide pack, so you can just have it. If you have some questions, hopefully we'll have some time at the end, but I'll be quick. So when we talk about competence, I like talking about competence equilibrium because in those countries that have weak competence standards and enforcements, what we found is low innovation, underinvestment in training and quality, and really a price-led business. In those countries where we have strong competence and standard enforcements, they benefit from value-led businesses, better than normal innovation, and really consolidation of the employment standards. For consultancy roles in the UK, we're okay, but for trades, it's pretty much all over the place. Have you seen the web of blame that was shown at the Grenfell final inquiry? Nod, or have some of you seen that? Yeah, it's pretty horrific, but I took inspiration from the web of blame and I created an installer competence skills map, and it's chaos. So when I joined, I'd never really worked in skills before, and this is what I saw, and it was really confusing. I didn't know where to start, who to speak to. They all connected in different ways, and what I've tried to do is clear that confusion. So I've got a brick wall analogy. It's very basic, and I'm sorry, but it's how I work. And the idea is that if this is the brick wall on the side of your house, today, our brick wall on the side of our competence house is structurally unsound. And the reason why is we all focus on the solutions. So if I said to you, what is competence for you? Some people might say it's my vocational qualification, my apprenticeship, my CSCS card, my whatever. But actually, that's not what we're trying to do here, because people who sometimes set the standards for a vocational qualification may be completely different to the people who are setting the standards for an apprenticeship. And they're completely different to the people managing the card schemes. And then you've got training providers running their own training, completely disconnected. What we're trying to do is dig down to that first layer of rotten brick and set the skills, knowledge, experience, and behaviours for the whole of our industry. And that will then feed through the skills system, so that no matter which route you take, whether it's an apprenticeship or a degree, you come out the other side with the same competence. Does that make sense? I hope so. Some of you are nodding, some of you are looking at me blankly. But the Industry Competence Steering Group has just launched, and I wanted to show you this because not all of you are installers, some of you are engineers, some of you are program managers, project managers, and I wanted you to see this because there's about 1,000 people in the Industry Competence Steering Group today working on creating competence frameworks for all these roles. It's supported by the Building Safety Regulator. So this work has been going on for about it must be longer than that. About 5-6 years, but we're really ramping up now in installers. This is how it works today. So we have the Building Safety Regulator set up. We have a committee that focuses on competence for our industry, and we sit under super sectors. Sector-led Group 10 is working on installer competence. One of the other things we've done is try to align with all these competence programs. Like I said, fix that first layer of brick. So these are all the programs we work with, and the Construction Leadership Council supports this work. So I'm going to show you very quickly our installer competence program so you can get a bit of an understanding of what we're trying to do. We consider an installer competence framework to be made up of these documents. So a strategy, explaining why we're doing this, a skills, knowledge, experience, behaviour statement on a page. Let's make it simple for these people, please. A route to competence, showing how we're entering industry and how we plan on gaining competence, and then an implementation plan on how we're going to implement that in the skills system. This is our program here, and we've broken it down into 5 super sectors. As I said, there's 130 different sector groups, so about 600 people working on this at the moment. I'm going to run through it really quickly, but this is Envelope, and it's led by Neville Grunwald of Waits. Everyone in green, we've created our competence framework, and we're working on implementing it at the moment. Everything in orange, we're working on creating those 4 documents. And everything in white, we are trying to set up and run. It can take a really long time to do just one, let alone 130. Here's engineering services. We've got interiors. We've got civils, which is where tunnel skills sits, and it's again led by Alistair Reisner of Seeker. And then we've got construct, a lot of tie-in with the civils work as well. So there's a lot of kind of cross-pollination there. So I'm going to give you an example, because I know I've just thrown a lot of information at you, but what we did on rain screen cladding. So rain screen is the stuff that burnt at Grenfell, right? And when I started on this, the rain screen standard was tied up in a roofing standard. So you had to be a roofer to install rain screen cladding. And it was factually incorrect. So the people who were trained to install rain screen cladding were trained in the wrong stuff. It was so bad. So we got involved and we set out the gap analysis, which was saying where are the problems, like I've just told you. We set up a working group. We drafted what skills, knowledge, experience, behaviours look like for rain screen cladders. And now we are implementing it. So we've updated the standards, we've unlocked funding, we're upskilling the whole industry, all the experienced workers at the moment, so that they can be competent in installing rain screen cladding. We've worked with CSCS on industry accreditation cards to tackle that issue, so there's experienced workers can continue to work in industry today. We're also working with MHCLG on the cladding remediation program. So we're doing all of this just for rain screen cladding, but we plan on doing the same with all the sector groups. My last slide is about the CLC webpage. All of this is on that page, but you can also have the presentation material, I think, Sam, is that right? Yeah. So that's all I wanted to talk to you about. I would love for you to ask me anything you want. That's a lot of info, but go for it. Any thoughts? Any questions?
Just one for me then. So what's the key takeaway for people here? What do you want from the people attending here to support the scheme?
We would love for you to get involved in the sector group with Tunnel Skills. We would love for some representation from all of you. It's a lot of work, as you can see, and we need your support in this. And we need some of these white boxes filled. So if you have contacts, people you want to get involved, you yourself want to get involved, we desperately need you involved. So get involved. And also talk about us when we're not in the room. You now know about this information. We'd love for you to talk about it, understand it, and yeah, get involved.
From a tunnel skill point of view, we're looking for help to do the
All right.
this is something that we're trying to do.
So the tunnel skills is the conduit then into this.
If people want to get involved, or you've got someone in your organisation you think might be interested in doing this on the side of their day job, because we're all doing it on the side of our day job, we need more people to come along now. Because at the moment, it's for us.
Okay.
So that's part of the reason for this. It's an appeal for assistance.
Does that make sense? Does anybody want to get involved? Do you want to lift your hand now? I'd love it. No one's lifting their hand. Ian.
But probably Ian would be a good point of contact. Most people know Ian, so.
Yeah, we'd love for you to get involved. Oh.
I want to make a comment rather than...
Oh, you don't want to get involved? Oh, okay.
I was called, wasn't I? Yeah. This is a huge project you've got, right?
Yeah.
And the complexity is mind-boggling, and you're just thinking, of course, of high-rise buildings and fire cladding systems. Of course, that's a model then for something that ripples through the industry. Right? So, but it's huge. And I mean, from our experience, from what we know, competence of skilled operators, right, is critical. Whether it be simulator training or training, and there are organisations internationally that are trying to establish these things. So I think that's always been a conflict for us, for some of us, with tunnel skills, plus the sort of other groups that we lead in Europe or internationally. And of course, we have to actually bring them all together, right? Because actually there's some really good work being done, not in the UK, but in other countries, but which actually involve the UK.
Australia have a great skill system, yeah.
So the question I've got really is, how do we harmonise that? How do we bring these other groups that are doing great work into the tunnel skills program?
Yeah, it's a great chat. I think you need to get involved and come and tell us about all these great things that you're doing. But no, it's good. I feel like this is actually the biggest collaboration program across industry, and in that, people are bringing some incredible ideas, incredible thoughts. I learned of the Australian skill system through a colleague who's working on the glazing competence framework randomly, and now we're engaging with the Australian skills system, trying to understand how they do it. They work on a modular approach. What is the great stuff we could take from Germany, from Denmark, and bring it into this country? But actually, what's more fascinating for me is that we're learning from each other in this program. We've got people talking to each other who wouldn't normally engage, and are now working at how they can align their work and make it applicable for everyone on site. And long term, once we find common skills, knowledge, experience and behaviours across the sectors, we can unlock funding for targeted training for all those individuals, rather than, at the moment, it's very isolated. It's very isolated. Why are those people not talking? Why haven't they work in the same building, So yeah, I would love to hear more about some of the ideas you have, so please do get in touch with Ian.
Yeah, I'm not an expert, but the latest specification for time, which has been produced by BTS, the 4th edition, there's a whole chapter on competency. So when you read that and the level of detail that's required for operatives now to be working, it's forcing the contractor to actually have that level of competency for his workforce. And basically, the new contracts which are coming out should be working to the 4th edition of BTS test. So I think that the tunneling industry is pretty well, set to work, in getting competency for its workforce.
Amazing, that's really good to know. I also have a personal thing. I want to enable installers and trades to own their own competence and not be told what to do by the higher powers. So a lot of what we're doing is flipping the narrative. We ask Building Safety Regulator, the Construction Leadership Council, CITB, IFA, all these organisations to help and support, not tell us what to do. We will own our own competence. We will tell you what competence looks like, and we will say no when you pass the design down to somebody who shouldn't be designing, as an example. So it's a real drive for me to flip that narrative, and because the installer program is the best of all of them and it's so massive, it's getting really good traction and people are listening to installers, which is really nice.
Okay, if anybody has any more questions, you've got Ian or Faye afterwards, but I'd like to give Faye a round of applause coming up to speak to us. Thank you very much. Okay, that brings us on to our evening presentation, which is on the use of ground freezing for cross-passage construction on HS2. So we have three speakers. Hammad, tunnel agent from STRABAG. She brings diverse experience from working within a specialised tunnelling consultancy to self-delivery and client positions, and has contributed to noteworthy projects including Crossrail. Experience in a wide range of tunnelling techniques ranging from sprayed concrete to tunnel boring machine assembly launch to traditional tunnelling by hand. She now serves as tunnel agent, leading the construction of 20 cross passages and 4 shaft to tunnel connections. Ella champions the promotion of best practice, co-authored a technical paper on innovative tunnel design and construction, and actively mentors peers to foster industry growth. Her contributions to the BTS and UN Women UK reflect her commitment to inclusivity and diversity in tunnelling. Recognised for her technical expertise, innovation and leadership, Ella continues to drive improvements in the tunnelling industry. Following Ella will be Phil Allvey, Tunnel Engineering Manager for STRABAG UK. He's been in this position since 2020 and has held the position of Tunnel Engineering Manager for the HS2 2 project, overseeing 2 TBM tunnels and cross-passage construction. Prior to this role, he served as an engineering lead on the London Bank Station upgrade project, which involved the integration of SCL and squarework tunnels with operational underground tunnels. Phil achieved charter status through his design and geotechnical contributions to projects such as London Power Tunnels 2, Thames Tideway, and other significant UK-based initiatives. And our third speaker is Dave Terry, Lead Tunnel Engineering Manager, SCS JV. Dave, working for LBA, is the Lead Tunnelling Manager for SCS JV construction of the HS2 London tunnels. He is a Fellow of ICE and IOM3 and a Chartered Engineer. His experience includes production supervision and engineering roles on numerous TBM, SCL, handwork and drill and blast driven tunnels in a 30-year career in tunnelling. So our first speaker will be Ella. Could you see if John, if you... Please.
If anyone does feel the need to have a dance, leave by the back door. Won't be offended, don't worry. Good evening, everyone. Thanks for coming along. So we're going to talk about the cross-passage construction using ground freezing on SCS. But, Mr. Chair, if I'm permitted, I'd like to break from convention for a little while, and that's pick up on the logo on the right-hand side of the slide. So the team that's presenting to you today, and there's probably some in the audience, were the Tunnelling Team of the Year at the NC Awards last week. So congratulations to all. Bit of a shameless plug, but hey. Right, so I'm going to talk about, I've really got the easy bit tonight. I'm going to hand over to Phil and Ella, but I'm going to talk about an introduction to the project. And I'm going to talk about the start of the sort of evolution of the cross passages and the corresponding risk management. This includes the initial evaluation of the ground conditions and how these were incorporated into the ECI phase, or as HS2 calls it, the stage 1 phase of the works. I'm also going to talk very briefly about the structure of the team. Right, HS2 Area South works. All the London tunnels have been undertaken by the JV of Skanska, Costain and STRABAG. We're supported by our design house, which is a JV of Arup, Tipsa and STRABAG. For the cross-passage works, we've also engaged RDMI for the ground freezing and WJ groundwater. And I'll have to apologise in advance, there are numerous suppliers who we could have named, but I have only got another 35 minutes. So if I haven't mentioned you, apologies. But so our works comprise everything from the southern end of the Colne Valley Viaduct through to the station approach at Euston. We passed through Old Oak Common Station, contract S4, which has been delivered by Balfour Beatty Bonsi. 40 kilometres of twin-board tunnels, an upline and a downline tunnel, approximately 1 kilometre of large diameter SCL, 7 ventilation intervention shafts, a diaphragm wall crossover box, various embankments, bridges, etc. However, the bit we want to focus on, wrong one, is Northolt Tunnels West. So the Northolt Tunnels West, which is at the start of the red box, starts at the West Ruislip portal where it dives underground, passes through South Ruislip shaft, Mandeville Road shaft, before getting to Green Park Way shaft where the TBMs are recovered. And along Northolt Tunnels West and the other tunnels we're constructing, several cross passages for escape and intervention purposes. There are 20 along Northolt Tunnels West, and following this initial evaluation of the ground conditions, all of them needed some form of treatment, both to manage the flow of groundwater into the excavation and also to provide stability in the granular soils. So the initial bet, 13 were labelled as using artificial ground freezing, and 6 were designed to be constructed using a combination of dewatering or depressurisation. Now, you'll notice that 13 plus 6 does not equal 20. So at the time, one cross passage, the last one we get to, cross passage 15, is still in abeyance, but the likelihood is we will undertake that without ground freezing or any form of groundwater control. So very, very simply put, the cross passage is constructed using a sprayed concrete primary lining, sheet waterproof membrane and a cast in situ secondary lining. I'm not going to say any more about delivery of the works because I don't want to steal Ella's thunder. So a bit about the geotechnical context. That shows a typical cross-section through the cross passage and a traditional borehole sticks. You can see the orange there is indicates significant sand layer. In more detail, so the slide at the top, the graphic at the top, shows the profile of the tunnel. It starts off in the Thames group, goes through the Lambeth group and skims along the top of the Seaford chalk. So in terms of geotechnical hazards, the Thames group is fairly benign, the Lambeth group is notoriously variable, and the Seaford chalk brings abrasive conditions and high water pressures. So the long section shows the London clay in the grey, the Lambeth group in the fairly beigey colour. Pick out the sand channels in yellow there, and the green is the chalk. Probably more interesting is the graphic at the bottom. So this was from the GIR. So what this shows is the geotechnical composition of the face along the drives. So on the left, I've superimposed a bit of a graphic of the running tunnel and then greyed out the bits so you're left with what the cross-passage face looks like. So you can see there, all along the route, we have very variable ground conditions. In some instances, full face of sand, in some instances, part chalk, part sand. As we get towards the right of the graphic, we leave the Lambeth group and get back towards the London clay. Very variable ground conditions. So a bit about pre-contract planning, how all this started. So this is like a trail of risk management, if you like. Started off at the pre-contract or stage 1 phase. So the principle behind stage 1 was to provide a cost for the scheme and also to develop our construction methods. So using our initial GI, we identified significant sand channels, we identified the presence of the upland formation, and we identified some of the hazards within the chalk. So to communicate these conditions and to start establishing a budget for the works, we categorised the cross passages. So these range from Category 1, which was the cross passages fully in clay. Category 2, where it's in the Lambeth group but not influenced by the lower aquifer. Category 3 in the Lambeth group, influenced by the aquifer. And Category 4, which was actually within the lower aquifer. What this enabled us to do was to start building up this picture, if you like, where we could start defining the treatments necessary and start putting a budget to them. Now, obviously the treatment assigned to the various cross passages were a function of the ground conditions, yeah, fairly obviously, but also the availability of the surface access and any work that needed doing to enable the access, bearing in mind that most of our alignment is under an operational railway corridor. This information was scheduled out and then was included in our stage 1 price. So again, we're building up this picture of the cross passages to end up in a price. So concurrently with this geotechnical risk assessment, we also had to position the cross passages along the route. So the graphic at the bottom shows an extract from the high-speed 2 technical standard spatial requirements, which governs the spacing of the cross passages in relation to ventilation shafts and each other. What this did, this identified several gaps in the ground investigation where further SI was needed or would prove beneficial to ascertain the prevailing ground conditions at each location. So this was done in 2020. We used sonic borehole techniques to try and maximise the core recovery in the granular soils, and this supplemented the work we did in 2017 and the further SI we did in 2018/19. Phil's going to talk a bit more about the verification of the ground conditions in situ, so I'm not going to say much more about this. I would like to say something about the team structure though. So, fairly conventionally, NTW, as are the other engineering teams on the project, set up with a delivery and an engineering team. Now, we thought long and hard about how to best represent delivery versus engineering. That's the best we could come up with. So you can judge for yourselves who is who. It's a fairly conventional approach, really. The engineering teams are a function of the overall SCS technical function, which is set up to be independent from delivery. So we adapted this very slightly to increase the engineering ties with a QA team, as opposed to having a completely separate QA function and a completely separate technical assurance function. We tried to integrate this a bit to fulfill the role of the HS2 lead designer, the duties of which are listed on the slide. The important one from the construction of the cross passages that we've taken forward into the actual delivery of the works is the one we've highlighted at the bottom, which is assuring that any changes due to ground conditions are incorporated into the design. So, on that note, I will hand over to Phil, who's going to talk a lot more about the design and the engineering.
Thank you, Dave. So yes, I'm going to go on to talk a bit more about the design and then a bit more about the engineering afterwards. So starting off then, we knew we had a lot of sand, so we needed to look at the best methods to stabilise the soil. And we really had the three options here, which were the permeation grouting, the ground freezing, or the jet grouting. So jet grouting we could pretty much rule out straight away because we didn't have surface access. We're in central London. We then had the permeation grouting. However, we're a bit concerned about the efficacy of this method because the soils consist of very fine silty sands, so the ability of the grout to actually penetrate through these soils could be limited. And actually on other projects, it was shown to have limited effectiveness in these sort of conditions. So that meant that freezing was progressed as our chosen option. Freezing is typically seen as a last resort due to cost. However, Ella will present later in the delivery slides why this was comparable to the other methods. So the chosen method we had to work with the segments around the cross passage. So we had the innovative special segments which we used, and this consists of tension rods both above and below the opening embedded within the segment. And you can see how these perform under loading as some of the slides here. And this replaces the traditional temporary works frame. So it's a very sleek solution, as can be seen in the right-hand picture, that you wouldn't even know that it is there. So it saves a lot in terms of tunnel space. So this next slide really just shows how these special segments are actually installed. So the dowels and the rods are manually installed within the casing. They're then all put together, so the special segments are combined together. The bolts are torqued up, and then the bolts then need to be encased in resin. And this resin provides encasement both for loading and durability purposes. So a bit more about the detailed design. So as part of the detailed design, we needed to verify the properties of the frozen soil. And this was done in the laboratory rather than undergo impractical and expensive in situ testing. So parameters such as the compressive strength and also the frost heave pressure were looked at, and they were fed back into the FE model to confirm that the ground freezing would actually work. So the ethos of the design was that anything above axis level needed to be frozen, needed to be sort of supported. And this was supported with a 2-meter thick freeze wall, which had an average temperature of -10 degrees. The innovation also was to incorporate sacrificial drill zones into the special segments, which I've shown. And through this, we could insert the 30 freeze pipes or so that were needed to form this ice body. And these were typically installed at 1 to 2 meter spacings, and they could extend up to 18 meters in length. The brine is then circulated through these freeze pipes at approximately -32 degrees, and this is a closed system, so there's no impact to the soils directly. Okay, so I now want to go on to talk a little bit about the engineering and how we involve the other teams as well. And this involves design management, data review, and I then want to go on to talk about the res, so really 3 aspects of the engineering team. So the first one then is design management. So freeze pipe design must consider the TBM ring roll, which can move plus or minus 100 mil, and also the horizontal and vertical deviation of the tunnels, which can move by 150 mil. So they will never be in their design position. And this means that each cross passage has its own unique freeze pipe layout. And this is because otherwise we could have clashes between the segmental joints or the non-drill zones. So the pictures above show the tolerances and how the position of the joints and the cross passage can actually change from its original design position. We also need to remodel the center line of the cross passage because of this horizontal or vertical deviation. And this needs to be updated and put into the Amberg model, which is used as part of the SCL profile control. Additionally to this, there's thermal calculations that are performed for every specific cross passage because each cross passage, as you've seen, has unique soil properties. So this will change the freeze time. Following this, we also need a Cat 3 check to confirm that the freeze pipe layout will successfully result in a closed freeze ring. Sorry, moved on. And just to show again, this is what it looks like when it freezes around the downline tunnel. You can see that this, with the zone here, this is kind of the pinch point of when the freeze body actually forms. Other excavation checks that we need are checking the segmental steps, looking at the resin grouting, which I've also showed you already, and then also a key stage is the geological verification. So I want to spend a little bit of time on this because this is quite important for the process. So as the TBM passes the cross passage, which you can see in the diagram in the top there, you can see that one of the TBMs has already gone past, with the other TBM about to go past as well. But as soon as the TBM goes past, we'll take a spoil sample from the belt, and then we'll do a PST test from this to confirm the granularity. If the granularity differs significantly from the design, we'll then accelerate the probing process with our subcontractors. And by probing, I mean we'll do hand probing through the grout sockets using a preventer in a typical probing array that you can see there. And this is really to confirm the stratigraphy. So in some cases, we actually found that there was more sand and it varied from the design model. And we had to switch from dewatering to ground freezing. And by doing this early, there was no program impact, because you have to remember that it can take some 40 days or so to actually form the ice body. So this was key to prevent any program delays. Okay, and then want to look at the second item that the engineering team and the other subcontractors look at, and that is the data review. And starting it off with the verification of the soil temperature around the cross passage. So there's 3 to 4 temperature pipes around the cross passage, and each of these temperature pipes has sensors every 0.5 to 1 meter along it. The output that you can see in the left-hand graph is one of these temperature pipes with all of the sensors recording the temperature. You can see that the temperature goes down as the brine circulates, with the brine temperature at the bottom there. The target average temperature is minus 10 degrees. There's also temperature sensors installed in the lining, both on the upline and the downline tunnel, and this has to reach a minimum target temperature of minus 2 degrees. Additionally to this, a drainage pipe with a gauge is installed in the middle of the cross passage, and this is critical to identify freeze body closing, because as the pressure builds up, it identifies that the ice is forming around the cross passage, and this pressure can then be released when we open a valve. And this is critical to confirm that we have full closure, and then we can actually open up the cross passage to begin excavation works. So this next slide is just to show how the temperature and the ice body change with time. So you can note that during the freeze-up stage, the thickness by the blue line increases by up to 2 meters, and then we also have our average temperature increasing to minus 10 degrees. Interestingly, when we open up the cross passage, you can see that the temperature drops off, and so does the freeze thickness straight away. It then stabilizes throughout the waterproofing and secondary lining stages. And then once we've achieved our desired strength in the secondary lining, we can strike the shutters and move on to the next cross passage. Another key aspect of some of the data we review is the monitoring data. So before we start any works, we need both surface and in-tunnel monitoring within the cross passage. For in-tunnel monitoring, we have 5 arrays installed on the heavy and special segments. And as the ice body expands, we have convergence moving towards the inside of the tunnel. An FE model here shows one of the deflection profiles. And from the graph below, you can see that as the ice forms, the convergence moves, and we have the 2 chords adjacent to the cross passage opening showing the most movement. And different geologies will produce different frost heave expansions. So for example, if we have more cohesive soils, we typically get more convergence. Then as we begin excavation and SEL works, you can see that this heats up the ice body and the convergence rapidly drops off. So the segments start to move back to their original position. Just one thing to note as well is that if we do have too much excessive movement, we will hold what's called a management action team meeting, and that's when we have a trigger breach. And if we had, for example, an amber or red trigger, we might take mitigation steps, such as to cut the segments early to release some of the stress. So then finally, when we switch off the freeze, as can be seen by the green dotted line, you'll see that the convergence returns back to its normal level, and the ovalization of the tunnel starts to return back to what it was originally. For surface monitoring, on the right-hand side, we have transects that are set up above the cross passages. And you can see again that as the ice body forms, we have heave on the surface. During cross-passage excavation, this heave stabilizes, and then finally, when we have the ground freezing switch off, it starts to return back to its normal value. And it will then stabilize, at which point we can look to decommission once we have proven 2 millimeters per annum. Okay, so that's looked at some of the data review that we look at. The third item as part of the engineering function is to consider the required excavation and support sheet, that's the RES. So the RES ensures compliance with design and allows modification of the sequence to varying conditions, and it's signed by both the engineering and the delivery team. We have hold points in the RES, which dictate critical items that must be followed before we move on to the next excavation stage. So rather than talk to you about what a res is, I want to show you a couple of examples of how we use the res to change sequence. So the first example will be the use of real-time monitoring to adjust sequence, and then the second one will be when we have adherence issues or a geological challenge. So on the first one, I want to show how we use monitoring to change this sequence. So the design prescribed either an excavation split face or a temporary invert when we were at the collar sections or excavating near the tunnels. And this was to prevent excessive deformation. So we wanted to change from this prescribed method to make this to a toolbox item. So we needed to prove to the designer that deflections could be kept below predictions and below trigger levels. And to do this, we used the innovative Wiesen system. And this is wireless tilt meters, which are installed on the cross passage in the arrays. So you have 5 arrays, like we've seen previously, and you have tilt meters installed in the middle of the segment. And you get the rotation around the joint, which as a vector by trigonometry is converted to a displacement movement. And the real advantage of this is that it's high resolution and there's no line of sight needed. So we could install this below the platforms, or if ventilation bagging was in the way, it wasn't an issue here. And it provides us with almost real-time data. So the question is, how did we use this to define our excavation sequence? And we did this by defining a toolbox trigger. So this was set to half the green triggers, with the green to red set on ovalization. Toolbox trigger was set at 16 millimeters. So this slide is just to show you how we react to a trigger breach and a non-trigger breach. So on the left-hand side, you can see that all the chords have remained below the 16 millimeter toolbox trigger, so we could continue as normal with the top heading and invert excavation. However, on the right-hand side, you can see that one of the chords has gone above the toolbox trigger. So this would mean we would need to implement one of our toolbox items here to prevent further excessive convergence, such as the temporary invert, which would involve more breaking out, of course, or we might have to split the heading as well. So the question is, how did we manage this as well? And it comes back to the res. We have a whole point in the res that states you cannot move on to the next excavation advance until you have checked and confirmed that the toolbox trigger has not been breached. So I want to move on to a real-life example here of how we did the excavation. So let's look at the bat mining sequence next to the collar. So this is the enlargement where we might have the prescriptive measure of doing a split heading if we had 2 excessive deformations. So the slides I'm going to show you indicate a real-time sequence of how we would react as the advances progress. So you'll see the picture in the top-hand corner there, and then the excavation sequence and the output of the Wiesen system, which shows deformation against time in the bottom right there. So this will be a better indication of how the deformation we get on each advance. Okay, so let's start with advance 7 then, as we would do real time. The picture at the top there shows the advance, and then on the left it shows where we are in the sequence, and when we have the output of the Wiesen system. And you can see at this stage we have very low movements, only 3 mil corresponding to this advance. So this would mean we have not breached a whole point, and we can move on to the next advanced stage, which would be advance 8. So we continue with our live process here, and this is our excavation directly behind the tunnel segments, the top heading. This is where we correspond to the most movement, but again, we have not breached the toolbox trigger of 16 millimeters. So we can continue as normal without splitting the face. And we would then carry on to our 2 inverts, which would be advance 9, and then finally advance 10, which is next to the tunnel segments. So we can see that during the 2 inverts, the deflection is relatively low. So once you have the top heading in, this acts to stabilize the segments. So hopefully this has shown you how we use the res and this automatic system to define our advanced sequences. So the next example I want to show you is how we might change the res to ground conditions. So this example in the first cross passage where we had SCL adherence issues. So this is different from fallout. It's not a fallout of the ground. It's simply the SCL bonding to the sand and not being able to stick to it, essentially. So the mechanism from this was that the partially frozen sand was not strong enough to support the SCL, it'd warm up, and that would mean the SCL would fall off as it was applied. So going forward, we needed to do two things to prevent this happening, and that was to reduce the initial mass of SCL being applied, and also to reduce the exposure time of the sand to keep it stiffer and frozen for longer. So we did this by implementing changes in the res, first of which was one of them which we could use was a P1 and P2 layer. That was to reduce the weight of SCL going onto the crown. So we'd initially apply a thinner layer of perhaps 50 mil, and then carry on with other works and top this up afterwards to full profile afterwards. We could also do other things, which was to prevent the exposure of the sand, and that was to either do a top heading and an invert, reduce the advance length, or do a face subdivision. And all of these items would prevent the sand warming up, and it would keep it stiffer, which would mean it would hold the SCL. Other things that were done at the same time as this were using rapid acting accelerators and batching the SCL at higher temperatures. So following this, we also wanted to make further optimizations. So we were in a fully frozen cross passage. So we wanted to work with the designers here, and we've successfully changed the lining thickness from 250 mil to 100 mil. And this, you can see the difference in the thickness on the left-hand side. And this had the obvious benefit that less mass was being applied to the crown, so you could hold the SCL better. And it's also obviously a massive saving in terms of SCL and also a considerable carbon saving. So once the SCL adherence issue was mitigated, we also wanted to look at other optimizations. So where we didn't have sand in the crown, we looked to increase the advance length. And this was because we're in a fully frozen ice body. So through the face logs and through the res, we could adjust the sequence. So for example, you see the full array of the cross-passage pictures there. But when we had clay in the crown, such as cross-passage 29, we could increase the advance lengths up to 2 meters, as was permissible by the design. So this had the advantage that would reduce cycle times and also increase productivity and reduce the amount of SCL wastage as well. So hopefully that gives you an overview of the res and some of the engineering functions along with the other subcontractors. I'm now going to pass you over to Ella, who will talk us through the delivery and construction.
Thank you. I'm going to kickstart the delivery section with pre-construction. So the cross-passage life cycle begins when the ground treatment starts, and this is followed by excavation and SCL works, waterproofing, secondary lining, permanent sealing works, cross-passage walkways and door frames. The cross-passage life cycle in terms of duration varies depending on the ground treatment that we choose. So you can see on the bars at the top, if we choose artificial ground freezing, the duration up until secondary lining completion is 152 days. If we choose dewatering depressurisation, that is reduced to 119 days. And finally, if there's no ground treatment, that's 50 days. In terms of risk management, so the initial temporary works design concept for the groundwater mitigation incorporated a hybrid solution. This involved 2 subcontractors working alongside each other, and it risked delays in terms of both time and cost. For us, we need to try and look at ways to mitigate this interface or completely eliminate it. So we looked at a couple of different processes, and I'm going to cover 2 for now. The first being lean application. So we applied regression analysis, which is a study of the time activity relationship, and we looked at the hybrid solution, first of all. So the hybrid solution was a combination of employment of artificial ground freezing in the crown and dewatering or depressurisation in the invert. And this solution was going to be implemented on a number of 10 cross passages. So when we looked at the regression analysis in terms of reducing this, we looked at a fully frozen solution instead, so eliminating the requirement of dewatering and depressurisation. You can see here that we've got the hybrid solution, and that is 170 days. And then after we applied regression analysis, we were able to reduce that to a fully frozen solution of 152 days. Of course, from a cost perspective or a cost analysis, while the construction and the design savings were very straightforward to identify, it was really essential for us to really consider the broader implication of implementing a fully frozen solution, considering the experience in the team. So we divided risk into two categories, the first being identified or time-related risk, and the second being unidentified or non-time related risk. We further broke this down into the probability of the delay occurring, and we looked at different scenarios, including the best case, most likely case, and worst case scenarios. It was quite clear to us from these two analyses, as well as others which I've not mentioned, that the fully frozen solution was the way to go, and we implemented this. So some of the benefits of this revised approach, including significant programme savings, like I've mentioned, it eliminated the interaction between the two methods and the two subcontractors, and it improved the tunnel logistics, including the interface management. One risk that was identified, and we decided to look into a bit further from this, was the interface between SCL and frozen ground. And we decided that we would need to look into creating a framework for this. So we developed a comprehensive framework which identified key risk areas and outlined mitigation strategies to address them. This structured approach ensured that all potential risks were systematically addressed and managed. We established 3 different stages for this comprehensive framework, the first being the peer review. So the peer review looked at 26 global publications, including projects. We also got in touch with international project teams, including meetings, and we got in touch with industry's experts. And overall, the conclusions from this peer review really offered us a solid understanding of the basics of SCL adhesion to frozen ground. Some of the conclusions that we came up with included the absence of adhesion measures on a lot of these projects in relation to mesh and other contingency measures. We also found that temperatures during SCL works could increase the temperature of the frozen ground and could cause issues with adhesion, so an appropriate accelerator needed to be considered. We also noted a lack of pre-production trials across all the projects that we looked at. And finally, and most importantly, we established that there was no correlation between early A strength development on an SCL panel and on frozen ground. So this last point that I mentioned is probably the most important one, and for that reason we established a conservative approach for this. So we adopted a correlation between early A strength development and shotcrete on frozen ground, and this basis was 10 MPa on a panel and 24 hours before we can allow personnel entry. So the information that I've just mentioned about the peer review, including the conclusions, these informed our mixed design trials. So we carried out SCL trials as you do on any SCL job, and these were carried out with CEMEX and NORMAT. So the cross passages, as you can see on the bottom right-hand side, are serviced by a surface setup. So we've got 4 40-ton CEMEX dry mix silos, and the concrete is batched directly into DG mixers that you can see in yellow on the bottom right-hand side. These trucks travel up to 8 kilometres within the tunnel to the cross-passage face, where the concrete is discharged into a concrete pump, and then along a concrete line directly to the robot. So we're using NORMAT pumps and NORMAT robots as well. Now, recognising the logistical challenges from travelling for that distance, it was clear to us that we needed to incorporate something to extend the open life of the concrete. And for us, that included incorporating a hydration control admixture. So this increased the open life to 6 hours, which is what we targeted. And this ensured the viability despite interface challenges, any breakdown risks and traffic delays were mitigated. In terms of the accelerator, we trialled 2. So we trialled the NORMAT TAMSHOT 80AF and the NORMAT TAMSHOT 110AF. And we tried different dosages at 6, 7 and 8%. We did choose 110 as well based on other projects using it in similar ground conditions, including Silvertown Tunnel. So now I move on to the construction, and I'm going to focus particularly on the use of ground treatment with ground freezing. So you'll see this timeline bar at the bottom of each slide indicating the different construction stages. So our enabling works start with the installation of working platforms. These working platforms are made up of steel modular units, and they need to be installed, dismantled and relocated with the TBM operations in mind. So we need to try and avoid impact on TBM operations, and we've been able to do this quite successfully so far. These platforms are particularly important from an interface management perspective. So we need to think about the other interface, other logistics that run through the tunnel. So for example, up here we've got the TBM passenger service vehicle, and we've got our cross-passage turntable. Here you've got the multi-service vehicle carrying the TBM tunnel rings, and you've got on the other side where we're building our cross-passage a deep sheet putting in secondary lining concrete. So it's a very tight area. You've got the tunnel conveyor and the ventilation also running. And we've also had to be quite dynamic with our approach. So the approach that we've used, for example, for the last 12 to 18 months will change. So we need to think about the future TBM disassembly works and some other shaft to tunnel connection works that we're doing. So to give you an idea of the proximity of the works, we've got a cross passage here, a cross passage here, and then in between them we've got an added connection that needs to be done and a roof connection. And you can imagine what that work would look like alongside the TBM disassembly and TBM operations running at the same time. You'll also see at the bottom, we've now been around 4 days installing the working platform. So moving on to the drilling works, which is the first element. With the drilling works, we start with coring, the segmental lining, the installation of standpipes, which you can see on the bottom left-hand side, and then the drilling of the freeze pipes themselves. So Phil already mentioned a bit more about the drilling, so I won't go into too much detail, but you can see here now 38 days in orange. So this activity typically takes up to that time, but we usually have been doing it a bit quicker than that. In terms of the freeze body, again, Phil has mentioned some of this already, but for us, particularly important is the installation of the insulation on both the upline and the downline tunnels. And you can see here, once the brine has gone through the closed circuit system, it's being circulated, and the freezing unit is installed, within a certain amount of time, there's no ice on the freeze pipes here, and you can see the ice development alongside. And I've added here 5 days, which is usually the freezing unit commissioning period, and 50 days, which is around the time it takes for the freeze body to develop. But I'll discuss that a bit more later. So moving on to the segmental removal. So our segmental opening is 3.1 metres by 1.9 metres. The segments are systematically removed, which enable a gradual assessment of the ground, and if necessary, the application of SCL as well. The sequencing of the opening typically follows a conservative approach, and this is based on anticipated ground conditions. So in terms of operations, if sand is anticipated above the tunnel access, we typically start with a top heading and invert, and otherwise we'll go with full face excavation. This approach specifically minimises the exposure of the ground to the tunnel temperatures, and also allows for the verification of the ground. We use 1 to 1.6 metre advanced lengths with extended lengths in the enlarged collar areas. And we use multiple passes of the shotcrete to ensure proper adhesion as well. So you can see the different phases above. And you can see at this point, we've allowed 29 days for the SCL works, including the segmental removal. Next, moving on to the waterproofing and secondary lining. So you can see on the infographic on the side, we begin with waterproofing the invert in its entirety, followed by secondary lining of the invert as well. We use a current shutter system. We've got 2 vault sections in yellow that are installed, and we've got 2 collar sections, as well as the waterproofing in the crown. And again, you can see here in dark blue, around 9 days for that. The waterproofing and secondary lining operations themselves are something that we need to really consider and think about carefully, especially the movement of the current shutter system. But you can see that the system works very well within the opening space that we've got. In the middle, we have our turntable. This allows us to remove the working platforms so that we can install this instead, and we can maneuver the current shutters on top of it. It means that we can get a head start on the next cross passage with a working platform. You can also see on the far right-hand side a completed cross passage with the secondary lining works and temporary fire doors. And you'll also notice now we've come to the point of the 152-day duration for the secondary lining works. I'll move on to lessons learned. So you remember earlier I mentioned about the 3 stages of the comprehensive framework that we developed. So I did mention earlier about the 24 hours and 10 MPa on a panel, this conservative approach that we adopted. This approach, of course, did impact our production, and so we really needed to find a way to reduce this and really look into this a bit more in a bit more detail and maybe develop the correlation ourselves. So what we did was, in the meantime, if geology allowed, the ground conditions allowed, we opted for a double heading and invert. And you can see that here. So by the time we've come and finished our second top heading and we've come back on ourselves to do the invert, we wouldn't have waited a full 24 hours. The impact would be a bit less, although we did wait the 24 hours. So what we did was we concluded that we needed to carry out simultaneous in situ testing. So we carried out in situ testing in the invert on freshly sprayed concrete in the invert, and you can see we did it in 3 different locations shown here, so left, centre and right. We carried out this testing and we were able to plot this on the graph that you can see on the bottom right hand side. The testing included penetrometer readings up to 1 hour and stud testing at 2, 3, 6, 10 and 12 hours. As well as carrying out the testing in situ, we also did this on a panel so that we had a comparison data set that we could look at. Once the sufficient data was collected and we did plot it, we were able to establish a correlation between the SCL panel and the in situ testing, which is something that we already established that we didn't have, but now we did. And we were able to reduce the requirement from 10 MPa and 24 hours to 2 MPa only, and we were able to achieve that in 2 to 3 hours. So that was a real big win for us. We also went a step further and compared the accelerator performance between initial on-site trials and the in situ testing, and you can see the 6% time shot 110 AF and the 8% time shot 110 AF, as well as the in situ testing that we did on site, all well above the J2 curve. And I'll just add as well here, you can see here where the sequence changed drastically, obviously depending on geology, once we implemented 2 MPa for personnel access, which really helped with our programme. So in terms of other elements of lessons learned for the sprayed concrete works, one of the first things is adhesion. So I mentioned at the beginning that we trialled both time shot 80 AF and 110 AF. Once we tried the 80 AF with, I think it was advanced 3 or 4 that we stopped, and we switched to 110. We found that 80 did not perform well on frozen ground, whereas 110 was high performing, and that worked really well for us. With the last advance as well, we reduced the percentage accelerator locally to avoid or reduce the rebound entrapment when we were exposing the tunnel rings on the other side. We did observe that the heat generated from the SCL would cause adhesion issues, which is something that we already noted and thought about from the peer review itself. So we did a couple of things to try and mitigate this or reduce this issue. So where we had where there was time between removing the insulation from the segments and actually opening up, if this time was too long, we would install extra drainage hose in the segmental lining, and this would allow us to eliminate any excess water before proceeding with the opening. I say this is a lesson learned because we did have an issue with this before where we left it too long and there was quite a lot of sludgy material behind. So this was lessons learned that we incorporate going forward. As per most of the SCL works, in the first few advances, this face was sealed as typically we do, but due to stability and heat generation, we actually removed this requirement, so we were not sealing the face on any of the frozen cross passages. Shotcrete application was carried out in multiple passes to ensure proper adhesion. And finally, in unfavourable ground conditions, we restricted the SCL work to 50 mil in the crown and shoulders initially and topped that up slowly so that we could get up to full thickness as the work continued. And that we found really helped with adhesion. And most notably, we had an 88% reduction in waiting time related to the early A strength testing correlation that we developed. So initially, it was quite a significant impact. In terms of the lessons learned for the ground freezing, Phil would have already mentioned that in the beginning, we have unique designs for each cross passage. So initially, this design was driven by geology only, and we had a fixed number of freeze pipes, temperature pipes, and water depressurisation pipes. What this meant is that the freeze time would really vary depending on geology. So you can see here between 40 and 90 days freeze time. From a production point of view, this didn't really work for us, and it made it quite difficult to really plan and to plan our works and also think about like the interface management that I'd mentioned earlier. So we looked at a revised approach where the design was driven by the geology and also the reduced freezing time. So what we wanted to do was reduce that range, so that wasn't between 40 and over 90 days. We wanted to reduce this, so reduce this between 40 and 50 days, and we installed extra pipes to target that duration. And you can see here all of these targets, all below 50, which is great, and the freeze pipe, extra freeze pipes, not being a significant amount. The amount of time to drill extra freeze pipes versus the amount of waiting time made sense to be able to do it this way, so that was a good saving for us. In terms of program, there's 3 colours here, so the first being blue, which is the planned, grey being the actual, and then green, which is the percentage delay. So this is the first SCL cross passage that we did. We'd planned for 37 days, which included the learning percentage performance values as well. With this cross passage, there was a lot to learn, and you'll notice that a lot of it is to do with adhesion issues in terms of the percentage delays, as well as in situ testing that we had to do, where we had to wait up to 24 hours. There was a few issues with plant as well, but notably it was mostly in situ testing. If I move on to the next one, you'll be able to see here with a cross passage 31, which is a few cross passages later. This is much, much better, and you'll see that the actual is like much more to the left than the planned. And you'll also notice that this one was planned for 33 days and we completed in 17 versus the previous one where we'd completed it 4 days ahead. The main difference with this one is that we didn't have to wait 24 hours for the frozen ground, so that was a big win for us. And we had some small pump issues in the beginning. Now, we noticed obviously from this the benefit of having that correlation, that data available to us in terms of program savings and delivery. And given the limited application of artificial ground freezing in the UK, for us it made sense to use the opportunity, the unique opportunity of doing 13 frozen cross passages to continue doing the testing, although we don't necessarily need it anymore, considering we have the correlation. So we have expanded testing to continue doing the in situ testing around the program, so it doesn't impact the program anymore, but we have continued to do that, so we've got a really good data set by the end of the job. So what's next? So far with the cross passages, and you'll see from here, from CP34 and working our way all the way along to CP15 at Green Park, all 20 cross passages, we've completed 11 freezing cross passages, 2 dewatered, 11 SCL as of last night, and 10 secondary lining. So it's really good progress within the team. However, there's a lot of scope still left to do. So we've got another 2 frozen cross passages to do, 3 dewatered, 9 SCL. We're only halfway through the secondary lining, so another 10. We've got 13 ceiling works to do, walkways, door frames, and then a number of tunnel to shaft connections, including added works. And you'll see that shown in blue, where we still need to carry out some work. I thought the 3D image on the right would be useful to show, to really give you an idea of the proximity of the works. So you'll see there we've got cross passage 28, we've got a roof connection that we need to do, and an added connection that we need to do, and all this within a 60-metre area. And of course, this is where things like the working platform and interface management come into use. So the ongoing construction of the cross passages, and I think as demonstrated through these slides from Phil and Dave, has proven very successful to date. There's been a clear willingness amongst the cross passage team and all the supporting functions to embrace the concept of lessons learned and really optimise the construction sequence. And I think this has been evident through a kind of transparent and open culture that we've got, especially with dynamic sequence changing that we've been doing. Now, particularly for the frozen cross passages, this commitment has been demonstrated through a lot of various actions. For example, going from the openness to go from a hybrid solution to a fully frozen solution. You know, the interface management that I've discussed, where we have to coordinate with the whole tunnelling team, and the production of the innovative data that I've went through as well. Especially where we're still producing data that isn't necessarily benefiting us right now, but we're doing it to benefit the industry as a whole by the end of the job. So I'd like to just close with the statement that's up on the screen, which is the accumulation of the ground freezing and SCL among the experience amongst the engineers, the operatives as well within the team, was a very limited asset to begin with and we really struggled with, but now has been a real significant asset to us. And this newfound expertise and real innovative benchmark data will be really invaluable for future UK projects, especially the workforce and engineers that we've got now with all this knowledge that they have. This really offers a solid understanding of risk management and best practices related to ground freezing. Thank you.
Microphones. Okay, you might have to shout to ask questions, but I thought that was a terrific, well-prepared, well-coordinated and well-presented presentation on a live job that's going on at the moment. So, questions, please. They're at the front there, yeah? Usually down there. Thanks.
Does it? Ah, right. Andy Sindel, semi-retired. That was a terrific talk. Right, John. It's brilliant. You were very quick on the permanent waterproof lining. I was wondering if you could just tell us a bit more about that. Was it sheeted? Was it sprayed? And above all, how did you join it into the segments to be permanently waterproof?
Do I just speak into that? We used a sheet waterproofing membrane from Renesco. We didn't use a sprayed membrane. And we used typical water bars, typically as we've used on other projects. So it wasn't anything different or anything special. It was just the normal sort of waterproofing membrane.
The microphone's not working.
No?
Maybe get a bit closer.
We just used a sheet waterproofing membrane. It was the same as usual projects, nothing special, typical water bars that we used Renesco to do that work. Yeah, that's it.
So I don't know how many you finished, but is it all drip-free now?
Yes.
Okay, one there and then we've got one over here.
Good evening. I'm Steve Doran. I'm now retired, but in a previous lifetime I was a project technical manager for the Storebelt tunnels in Denmark, and we had some 29 cross passages beneath the Storebelt, which is connected to the Atlantic Ocean, of course. A couple of comments on the presentation. Firstly, with regard to adhesion of the shotcrete to the frozen surface, what we found was that we got a layer of condensation onto the frozen ground, and when you sprayed the shotcrete against it, the heat of hydration from the shotcrete melted that condensation, so you were left with a layer of water between the shotcrete and the frozen ground, and it consequently tended to fall off. And our solution to that was to hit the frozen ground with sort of a roofing felt type blowtorch, just to melt the condensation before we sprayed the concrete. And we then got the adhesion that you wanted. And you needed, in our view, to have a fairly thick layer. The initial layer we put in was some 100 millimetres, because what you're trying to do is to get a sufficient thickness of shotcrete in the first layer so that it gets its initial set before it becomes frozen. And in that way you don't get the damage to the shotcrete lining. So they were the experience from that project. And I know you mentioned various papers that you read with regard to previous projects, and I'm just wondering whether Storebelt figured in your determinations in that regard.
Well, maybe I'll start by answering the question. So, With regards to the SCL adherence, I guess what we really found was when the sand started to warm up, that was when we had the issues that it would tend to fall out. So we typically didn't want to heat it up. We wanted to reduce the exposure times.
It was just basically showing the exposed surface with a fairly broad sort of a roofing felt type blowtorch, just to melt off the condensation before we sprayed it. We didn't try to thaw the ground out in any way, but it just wanted to melt away that layer of water from the condensation.
I think after pretty much the first advance, we seem to have resolved the issues actually, but you know, point taken on that. I guess there's different ways to solve the solution. And also on your comment on concrete degradation, so in the design we'd actually incorporated that 30 mil of it was sort of sacrificial, and we'd also looked at cores through the lining as well to confirm that we didn't have the sort of degradation that you're talking about.
Yeah, I mean, we cored our primary linings and did some petrographic testing on it, and we found very, very little damage due to the thawing effect of the freezing before it became frozen. I mean, the concept was to get its initial set before it became frozen by contact with the ground.
Okay, I think it sounds like we had similar results by different methodologies. Yeah.
Thank you.
Okay, over here.
Yeah, hi, David. In the excavation and support sequence and the program, you showed that you removed the breakout segments before, I think, before you excavated the last four steps in the sequence, and before you'd formed the collar. What's the reason for that? Wouldn't that have made the convergence in the breakout tunnel, wouldn't that have accentuated it a bit? Or have I got that wrong? Have I misinterpreted it?
I think that's maybe misinterpreted. So when we're approaching the other tunnel, we would never have removed the segments at that stage. It would have been cored perhaps, but then when we turned around, we're looking at the original entry point of the tunnel, and that's where we did the breakout enlargement of the collar section.
I just seen from the program, the breakout occurred on the program for RES steps before you actually reach the extrados of the lining.
No, that would have just been the coring, and then the excavation itself would have happened at the same time as us removing the segments. Yeah.
Okay, maybe I misinterpreted.
All right, I've got one question online here from Slav Litwin. Were there any lessons learned from occupational exposure to ground freezing process equipment to operators, installers, etc., or any particular injuries?
No.
Good news.
No, I think the other thing too is that the subcontractor that we're using, RDMI, very experienced subcontractor in this. We're using a closed circuit system, and there are a lot of safety measures and hazard identification meetings and things like that need to be done beforehand. So we've been able to do that successfully.
To any specific protection, PPE that was needed?
No specific PPE, no.
What we did do is, as the cross passage broke out, you obviously got the box of freeze pipes around you. That was all protected quite rigidly when we mined out through the segments. So there wasn't this direct interface between the mining gangs and the freeze pipes. It was all closed off, which worked quite well, I thought.
Yeah.
All right. Steve?
Steve Parker, Keystone Tunnelling. Thank you for that presentation. That was excellent, and thank you for sharing the lessons learned. I think we'll all take that away as beneficial to sharing with everybody, so thank you. Did you ever consider in the early days the strategy of SGI lining? And I'm thinking here, because you've got difficult ground, it doesn't change the dewatering or the ground freezing, but your excavation diameter would be a lot less with a 110 mil thick, say, SGI lining, which also is the primary lining and the finish lining. Did you consider that and look at the cost-benefit ratios? But mainly from a risk point of view, the excavation diameter is a lot less, and I wonder about the construction duration. even though the lining is initially more expensive.
So did we consider it in terms of a cost-benefit ratio? No. Did we consider it? Yes. But the problem we always had was the ground conditions, particularly on North Oxford and North West, are so adverse that we would have had to put lots of mitigation in to enable us to mine it.
Sorry, the ground freezing, and I'm not saying that would change at all.
Sorry, I've misunderstood.
So I'm just saying the lining, so I'm trying to say don't use SCL primary and secondary, or cast, primary or secondary cast, eliminate that. The SGI is the final lining, the only lining, and the excavation diameter is probably between 500 and 700, 800 millimetres less. So you line the tunnel with the SGI lining, the excavation is less, but the support to the ground is just the same as you did.
So I think my answer still applies, apart from the bit I misunderstood about the ground treatment. We didn't consider it in terms of cost-benefit ratio. We were unsure of the availability of SGI. That was always a consideration. And in the end, we adopted the SCL approach and the commensurate waterproofing and secondary lining.
Martin Preen, Coffee Technics. First of all, excellent presentation. My question's about the freezing. You didn't mention whether or not you surveyed the freeze holes, because obviously if the freeze holes, two freeze holes diverge, there's a danger of getting a gap in the freeze. Or did you sort of design that out by having loads of freeze holes? So did you survey the freeze holes? And secondly, again, you've not talked much about the thermal design. Did you compare the design freeze times and design freeze rates with what you actually achieved?
Yes, so we did survey the freeze holes and look for deviation, and then when they actually did the thermal calculations, that was, if there was any deviation, that was considered in the calculations as part of the freeze closure. And then the second part of the question was, what was that about the thermal?
Well, it's just really, given that you've obviously gathered so much really great information about experience with ground freezing for cross-passage in general and in UK conditions, you know, when you do a freeze design, you'll get at various different locations a predicted plot of temperature against time, for example. Have you done any exercise comparing how accurate the freeze design was compared to what was predicted?
Well, yes, we have done that. Normally, the predictions are fairly accurate. I mean, I'd say maybe 3 to 5 days out could be a maximum, but it kind of depends on the geology as well. If that varied from the design and we had a lot more clay, then perhaps it would take longer, and that's, you know, when we got to one of the 90-day freeze times that we saw in the presentation. But we're kind of in the process of doing that at the moment because we are still, you know, active tunnelling, so.
All right, got another question online from Anna Barbosa. Were the tunnel segments designed for the load case where the frozen mass caused the lining to converge? And if so, how were the loads determined before conditions on site were determined?
Yes, so they were calculated by a design house, so the freeze body was modelled on the lining and the deformation was assessed as well. And that's how they came up with the convergence levels as well and the trigger levels, because they were sure that the deformations would remain below those.
Okay, yeah, thanks. Another question?
David Hartwell, retired, failed. I was with Steve on Storebelt and was responsible for some of the cross-passage works, including quite a lot of dewatering, so I'm a bit biased. Did anyone consider lowering the tunnel alignment? Because your geology slide that you put up seemed to shout at me that said you've gone down fairly steeply and then you've stayed in the bloody horrible sand layers all the time. Why didn't you just go a bit deeper and keep away from the sand, stay in the chalk, gives you the option of a bit of grouting if you want, dewatering, stable ground. Was that considered?
So the long answer or the short answer? The short answer is it was considered. The problem we have with HS2 alignment, to take it deeper, you would have had to take much more land on surface to get the alignment back up to surface. We would have also had to deepen the shafts along the way, and the cost-benefit ratio didn't work out. With hindsight, and with another couple of things that happened that would probably make the subject of another presentation, it may have been a better plan, yes. That's a very honest answer.
Okay, question here.
Hello, Sophie Cannon. Unlike others in this room, I'm no expert in this field, but I really enjoyed your presentation. I thought you explained things extremely well. Obviously, you made savings on programme and STL, on carbon and all of the rest, but I'd like to know, what do you think was the greatest achievement of this, and what do you think the industry will take from it going forward?
I think we should all have a go at that one.
I think that's quite a difficult question, mainly because... can I move this? Okay. I think that's quite a difficult question, mainly because the achievements across the duration of what we've done so far have been honestly very substantial, and we've still got a lot of work to do, like I've shown on the remaining scope. But I think one of the main things is collaboration between the different teams. Being able to do what we're doing now with the cross passages, considering the TBM operations, the tunnel invert concrete, and then the future works that are coming up, I think it's quite remarkable, really, to be able to do that in the tight spaces that we've got. On top of that, too, I didn't really show on any of the slides, but we've got the civils interface at the top of the tunnel as well that we're doing, and we need to coordinate all of our logistics around that. And I think if that doesn't work, then really we wouldn't really have a presentation to go through today. So I think that's really, really critical. And I think the second probably really good achievement is just the experience in terms of freezing for the team that we've had. I did highlight it at the end in the closing statement around the asset that we've got now, but really it's something to really kind of think about, the sort of experience now that the UK industry has going forward, considering what we had in the beginning. Dave?
It's a really good question, that. I think for me, the greatest achievement is the ability of the team to stop and think and look at the detail, of which, I mean, you saw from Phil and Ella's presentation, the amount of detail you have to look at to get this right is incredible. To look at the detail, to pick holes in it where necessary, and to correct it for the next one. Because bearing in mind, there are probably 5 active work sites in the cross passages we've talked about, segment cutting, primary lining, waterproofing, secondary lining. All these are going on at the same time, and it all moves down the tunnel in a sequential fashion. In that environment, when programme is fairly key, the ability to step back and look at the detail and make amendments, tiny amendments that make a difference to the sequence, to me is a real win. So for me, the team.
Yeah, I would just reiterate that really, it's really the collaboration between the teams. I'm not sure the tunneling was always the difficult bit, it was the collaboration. The HS2 is a massive project, so it's good that all the teams were integrated and could cooperate together, and I guess that's why we were ultimately awarded the tunneling team of the year due to that collaboration. So.
Got that one in.
Did anyone notice the plug there?
Got a simple question online first. Have you tested the strength of the frozen ground?
In situ, no, we weren't going to do that because it's sort of impractical to transport ice cores from the tunnel. Yep. So we verified it, as I said, by the laboratory analysis, and we proved that we had the necessary compressive strength and Young's modulus, etc. from that, and that fed back into the design.
Right, thank you.
Yeah, Roster McNormet, great presentation from the three of you. Really, really excellent. Of course, you were plugging Normet quite a bit, so I'm really pleased for that. But I was interested. I visited the site, and thank you for that as well, Ella. But one of the things I left coming away with was the size of the opening in the running tunnels to the cross passages. And I just wonder whether that was limiting your excavation speed. I don't think it was limiting your spray concrete speed, but whether you could get a big enough bit of kit in there to rip that frozen ground out, whether it would have made a big difference. A second point is, I'm really interested to know if the spray concrete suffered in any way after being frozen. Was there any, was the spray concrete shown to continue to gain strength? And have you had the chance to see any long-term strengths from it? And my third point is that I think the contribution to the industry is really interesting, a good question. And from my point of view, the designed approach to use frozen ground in a planned approach, rather than what we normally use it for, to resurrect a mess up, a bit of a cock-up that we've made and collapse the ground, is really good. I think it's been a really good engineering solution, planned. Really good, well done.
I'll answer two parts of the question. I'll leave the other part for Dave and Phil. In terms of the speed with the opening, I think at the beginning we thought it would, but we were able to manage with it. We were able to fit a Brock 500 in there. So really, I don't think the issue was necessarily the size of the opening in the end. It was really the space outside of the opening. So where we've had the working platform, and I showed the robot, the excavator taking out the muck, and then you've got the de-cheese reversing in to take the material. That was the constraint rather than the opening size. And if the opening size was any bigger or we could go any quicker, we would have still been constrained because of the logistics to the tunnel. But I don't think I've mentioned, but like our quickest SCL works were, I think, 9 days in total. So with the size of the opening that we've got and the logistics, we're still managing to complete the full SCL cycle in 9 days. So if we didn't have logistics, it would be quicker. In terms of the contribution, could you repeat that, please?
It was a planned, designed approach to solve a problem, rather than what we normally use frozen ground is to resurrect a failure.
Yeah, I think, to be honest with you, I think as well, on previous projects I've worked on where previous project I worked on where we had to implement every toolbox item and then some after that and try and find, at no point did we consider ground freezing, for example. And I think at the time when that happened, it was mainly because no one in the team had ground freezing experience, whereas in the team that we've got now, our tunnel leads, they have ground freezing experience, and so I think the suggestion from them to look at that obviously was quite a positive thing. So I think going forward, between ourselves, between the different people that have had experience now, if there are toolbox items coming up or you're going on a new project and you're thinking about, you know, different ground treatment options, it'd be easier to consider that since you've got the experience. So yeah, I think that's the main reason why. And then the degradation partly for Phil, but the strength.
Degradation, yeah, I mean, we looked at cores through the line-in and we actually saw relatively little degradation, which was, I guess, quite surprising and impressive as well. And in terms of strengths, yeah, the cores performed as we would expect. You know, we did 28-day strength, 56-day. We do have some 90-day results, but it's not so critical for our works because the secondary lining goes in before that, but all performing as expected.
So just like to add to what Ella said about the industry and moving forward with ground freezing. So that's why I worked at Hull. So that's why I'm more than familiar with rescuing things. Hence the grey hair. It was very interesting because as part of the development of the freeze design and been a planned approach, when we first came up with the ground freeze, there was several cross passages that were part dewatered, part frozen. So we were freezing the crown and dewatering the invert. What we did, Ella did a very good cost-benefit analysis, and from a pure risk point of view, it actually made sense to completely freeze the full ring. So it almost went full circle from considering freeze as a rescue thing previously to this project. We actually adopted it as the ultimate mitigation. And what was really good is, so High Speed 2 have the independent technical expert panel, the ITEC, and they fully backed our approach of switching between this hybrid approach to the full ring. So it's really good.
Got one more online. Alex Smith, great presentation, thank you. What secondary lining concrete mixes are you using in the cross passages? Was this influenced by cross passage fireproofing requirements?
Yeah, I mean, secondary line and mix. They could have to fill you in the exact details, but yeah, we do consider fire design as well with the polypropylene fibres as usual to mitigate against, you know, explosive spalling. So, and with typical design strengths, really. I guess, I mean, you could also touch on the mix as well because you have to add additives as well because it has to travel some distance down the tunnel during the secondary line pours. What we have, you know, ultimately be 7 kilometres. So added additives like HCA to improve the life of the concrete.
Okay, any more questions from the floor? One at the back there.
I suppose I'll ask the obvious question, really. You've mentioned legacy a lot. It's a great project, a lot of lessons learnt. I presume you're going to write up the work you've done in some sort of technical paper or publication befitting of HS2's legacy programme. So there's something in writing for the years to come.
I think any one of us can answer this. The answer very, very simply is a yes. So we've already, and when Phil went out to Stockholm to the Sprayed Concrete 24 conference, was it, I think? So we've already presented it. We will write it up. Sorry, it wasn't Stockholm, it was Norway,
Oslo.
wasn't it? Oslo, sorry. Geography's terrible. But yes, we will be writing it up. Yeah. Yeah. There's also a plan to present it at WTC next year. So, yeah.
All right, well, can we all show our appreciation? The level of questions is excellent. Just a couple of slides and then we'll finish for the evening. Next one, please. Just a little note about Chris Hughes, someone I knew very well, and I'm sure a lot of you did, died suddenly in November. We just had a little celebration for him last week downstairs in the ICE bar. So Chris was head of Morgan, Sindel and Miller tunnelling for many years, particularly in the 90s and early 2000s. Okay. Yep, Ross and Normet sponsoring the drinks tonight. Thank you, Ross. And CK Tech. Sorry. And the food sponsored by CK Tech. Books are being delivered. Here is one here. Anyone wants to have a look at it? Quite a few people who spoke to me said they arrived at their doorstep, so they're on their way. And you can still order books at a cost of £65. Just go onto the BTS website. Lots of people are doing that as well. We still have some books available. Okay. Thursday the 16th of January, there is a talk on Tunnel Europe in Lyon-Turin project. The Great Challenge Through the Alps. So that'll be our first one in 2025. Next one, please. So this is one that come in. It's not one the BTS specifically, but we're promoting it. I think it'll be of interest to a lot of people, particularly the speaker. So it's Professor Lord Robert Mayer talking about unusual tunnel collapses, the role of geotechnical engineering. And that's on a Monday. It's in person on the 27th of January. Okay. And then our lecture for February is on Thursday the 13th. This is with combination with Min South Mining, and that's on the Woodsmith project. Yep. Harding Prize presentations. This is on Thursday the 20th of March. So BTS members will have seen information on that, looking for young tunnellers to prepare papers, and some fantastic material here if you've got any young tunnellers that want to put a paper in.
There's no use looking at me, mate.
Next one, please. Arabelle's out here. She was on the microphone. So she is the current chair of the Young Members BTS. Very active, lots of ideas, and looking for people to join and give some enthusiasm and energy. Now, I went to the conference last week, and there was some terrific presentations and very open minds. It was great to see. Okay, next slide. Yeah, if you want to scan that, how to get in touch, how to get involved with the BTS or the Young Members BTS. There's a QR code there. Yep, next please. The annual dinner. So the flyer will be issued in January. Bookings open from the 1st of February, and the date's slightly later this year. So it's normally the first Friday in May. So it is on Friday the 23rd of May this year. 23rd of May, same venue at the brewery. Okay, thank you. You won't be able to recognise that, but that is John Scully wishing you all Merry Christmas in his own inimitable style. Okay, next slide. Yeah, the book. Yeah, I mentioned that. Next slide. Is that it? Right, one more thing. So another Young Members initiative. They had a quiz held here last week in memory of, well, the topic was St Barbara's Day on the 4th of December. So Dickie Dexter's going to come down and present to the winning team. And there's a wonderful, fantastic trophy, hugely impressive.
I don't actually think all the teams here. In fact, I know one member of the team, Arabelle and Vantika. Yes, it's only you two here, I think. Unless, where's your other team player?
Have we got any cameras?
Oh, yeah. And the other the other team member that played for their team was my predecessor, Mr. Slogan. So, just good fun. The only rule I would say is on future, don't pick the night of the NCE Tunnel Awards and the SCS Christmas party. However, well done. Congratulations.
All right, so that concludes the evening, and just wish you all a happy Christmas and a prosperous 2025. All right, thank you.